Welcome everybody. It's a long walk from the keynote. Big applause. Thank you for being here. Come on, a little bit of energy. I know it's still the morning. Welcome. I am Bill Clayman. I am the co-founder and CEO of Apollo.us. You can take a look at what we do. But I'm also the program chair here for Data Center World. I'm a contributing editor to Data Center Knowledge. I've been a part of this organization for some time, and I've had a chance to sort of take over as the program chair about 4 years ago, and we've seen this conference just grow and do a lot of really extraordinary things. We're trying to make sure my mic is up a little bit. I don't know if we're gonna have time for questions today. I'll try and see if we can figure it out, but it's gonna be a lot of really great content. Before we begin, how many people in this room have been in the industry for 3 years or less? 3 years. Okay, 2? You're fresh off the boat. And first years over here. All right, cool. All right. So this is called the Data Center 101, a masterclass in digital infrastructure. Last year we did this in a room that was way too small, and then this year this is just right. Everybody's here, getting comfortable. We got some people walking in. The goal today is to learn about data centers. I think that's pretty straightforward, right? I'm going to do my best to arm you in the course of about 30 to 40 minutes with as much knowledge as I can around what is a data center, where do you put it, what stuff goes in it. And this is not an overly technical session, I promise, but this will teach you all of the critical components that go into a modern facility, right? We're going to talk about AI, liquid cooling, all the other stuff, but again, we are not going into the weeds. We're going to be covering more or less at a high level, but you're going to exit here much more equipped to walk around that expo floor hall, knowing what you're looking at instead of, hey, that thing is spinning and it's really neat. Imagine that Gordon Ramsay cooking an amazing Thanksgiving dinner in about 20 minutes. It's going to look great, but you'll have no idea what happened. That's okay. At least you know what the food is like. I'm really, really grateful that you're here today. Please, by all means, don't be shy. You can connect with me. I'd love to continue this conversation, but let's dive right in. We're here not because of ChatGPT, but it certainly is a driver of it, right? We have not seen any other piece of technology ever gain this type of adoption as this AI architecture, and I just want to make sure everyone understands there's no going back, right? This is not a step backwards ever, right? This is the new way that we're going to interact with data. And I just want everybody in this room to understand you are all users of generative AI. We've been trained for 30 years. September of 1998 was the first time you could ask Google a question. And ever since then, every single one of you has been conditioned to interact with data in a very specific way. A blue link. You ask a question, and you get a blue link. God forbid you end up on page 2 of Google. You're lost. That's like Mordor. You shouldn't be there, right? But you should find your information on page 1. But all of a sudden, what feels like almost overnight, if you go on Google or Bing right now and you ask a question, is it a blue link anymore? It's a generative AI response. Nothing has come close to the level of adoption of these technologies. And that is going to have a massive, massive impact on what we do, how we develop infrastructure, and so on. And obviously you heard from Wade, you've heard from Dave Bell from VoltaGrid, but power is one of the most critical aspects and one of the biggest barriers of entry into this industry. And I promise this is it as far as intro slides. We're going to go right into what data centers are and how this impacts it. But please take a look at this for a second. We have 5 gigawatts under construction right now in the United States with about 40 what is that, 2030 from Boston Consulting Group. Right now, we're taking about 2.53% of all U.S. energy. By 2030, we're scaling to up about 7.5 to 8%. There's this thing called Jevons paradox, okay? With efficiency gain come consumption, right? So that you kind of trail forward. For the first time in our industry, consumption is outpacing how efficient we are with this infrastructure. And we'll catch up, right? We'll get there, but this is extraordinary. Now, for those that are looking at this and are like 45 gigawatts, I don't know what that means. 1 gigawatt, city of 1 million people. 10 gigawatts, Los Angeles or New York will power that much. And 100 gigawatts are about 10% of all of the lights that are currently on any moment in the world. That's how much power we're talking about. 5 gigawatts under construction with another 45 to 50 in demand within 5 years. Just something to think about. And obviously, because of all of that. These new technologies, we're going to be really important, and we're going to be front and center, and it's why our industry is absolutely having a moment. Mainstream news, I think South Park did an episode called Deep Learning, which is about generative AI. It's scary, and it's really good. If there's a recommendation I do about South Park is very rare. I recommend that one episode because it's really interesting. So let's give you the textbook definition. What is a data center? Let's dive into it. I actually didn't have any caffeine. This is all natural energy because I love this industry. So let's get into this masterclass. Before we dive in really quick, they're everywhere. They're everywhere. These are no longer nondescript buildings. The latest report from Synergy Research Group, there's over 1,000 hyperscalers. Those are the big ones. They're the Google, Microsoft's, the big facilities, right? Over 1,000 in the world, about twice as many as there were about 6 years ago, and that continues to go up. S&P Global 451 Research is tracking 10,000 colo, and we'll talk about wholesale, what those are. We don't have to know what those are yet. We'll define what those terms mean, but basically there is a ton of them. So what is it? What is a facility? What is a data center, right? It's a purpose-built facility that is housing compute, storage, networking equipment, designed to meet capacity, reliability needs, and allowing companies to deliver applications, services to their customers and users. It could be a variety of different kinds of services, but that's it. That's what it is. It's a building that does some really cool stuff. No longer a nondescript warehouse in the middle of nowhere. Every second in a data center, every one of you with your cell phone in your pocket right now is communicating with a data center and doing this. Well, hopefully you're not like buying an iPhone right now, but if you are, I guess that's fine. Google searches, 145 items sold on Amazon, 10 iPhones per second. Apple downloads, Meta users, hours uploaded in video, and ChatGPT now with 400 million weekly active users. So every second in a data center, something extraordinary is happening. And when we look at the types, right, so this is something we talked about earlier. So there's a couple of different types of data centers out there. And you're going to hear this a lot in your career, in your industry. There's going to be several. So corporate-owned, enterprise. This is an enterprise facility. It's like Nike has a Nike data center. That's what they are. They own it. The challenge with some of those, and I got to keep this brief because we do have a lot of content, is they're not usually efficient. Data centers, their focus is, are the lights on? Great. I don't care if the PUE is 15. Power usage effectiveness, you want to kind of keep it close to 1 as you can. But they're not always as efficient. Some are, but not always all of them. Co-location, multi-tenant by rack and cage. This is somebody who says, I'd like just a rack or an entire row, for example, but you own the facility. Wholesale, single tenant built to suite. Think of it like a Compass or Digital Realty building for like a Google or for like a Microsoft. So Microsoft will go to them and says, this is what I need, these are the specs, you build it, you come in, and they'll go to a wholesale data center builder. Dedicated hosting provides rent server capacity. So I own the building, I own the racks, and I own the servers, and you get a chance to rent them out from me. It's pretty straightforward. Managed hosting is going to be very similar, except when you're renting that server from me, I also manage it for you. Right? I'll give you those managed services. I'll take care of it for you. All set. Shared hosting, again, very, very similar, but you share a capacity. So like one server, right? Carve it out into what are known as virtual machines. And each person can have maybe their own virtual machine for development, for applications, for testing, whatever the case might be. But dedicated, managed, and shared are usually owned. All the infrastructure is by me, and it's fully an OpEx. You don't have to pay anything just for the service. Hyperscale data centers, you know what those are. Those are the big ones. Those are the Microsoft, Apple's, those are the big facilities. This is a new one from last year. They're probably going to change the name, but I have to put it on there. AI factories. You're going to start hearing about it. I don't know if it's like a marketing-y kind of a term, but we're going to start to see the conversation on massive high-density facilities, and Wade talked about the design of that kind of architecture. Very much so. For private use, you know what's a good example? Elon Musk's XAI architecture with 100 GPUs. That is an AI factory. That's a really good example of that. We're going to be seeing facilities that are purpose-built, high levels of density, which we'll cover in a second, specifically for artificial intelligence. Let's take a look at what's inside. So you're inside of a data center, right? What you're looking in on a rack, right? What's inside of it? Servers, from mainframes to pizza boxes. A mainframe is like an IBM. Bigger, old school, green screen, but still very, very functional. We call them pizza box servers because that's what they look like. They're little pizza boxes. You put them in a rack. Very, very functional devices. Storage, network, other devices like KVMs where you're able to like pull a keyboard out, maybe access a rack, work on something there, for example. Consoles, tape libraries, and now GPUs, graphic processing units, NVIDIA, Intel, AMD. We will go into a little bit more details onto each of these pieces of IT hardware, but we're flying along. This is what you will find from an IT perspective inside of a facility. Let's talk about rack densities. Now, I actually have something very special for everyone. This is really, really fun to do. Hang on, bear with me here for a second. It's worth it, I promise. My friends at Vertiv gave me something really special to carry around with me. And lo and behold, I actually brought a real data center rack. Hang on. It comes with its own battery and power supply, which, of course it does. Trust me, this is worth it. Hang on. Oh, I hope you guys are ready for this. Always got. And there we go. You're going to see on the screen here, the door's open. Isn't this adorable? This is the cutest thing in the entire world. Oh my gosh, I absolutely love this thing. I'm going to pick it up for you so you can see it. This is the cold aisle. That's why it's blue. And this is the hot aisle. And that's why it's red. Cold goes in front. Hot air goes out back. Now, I just want to be very, very clear with you. You're going to stay right here with me. I just want to make sure I don't bump into you, little guy. My little rack. Vertiv was actually nice. They sent me a whole row, and it's kind of heavy, so I just brought one little guy. Now, for anyone who's been in this industry for just a year or so, I need to make something very, very clear with you about racks. Real racks are at least twice as big as this. I have to do my Zoolander impression, right? What is this, a data center for ants? That's it. I got it out of my system. But you're welcome to take a look at this. I think this thing is really, really neat. And it does represent, this is literally what a data center rack looks like. This is the cold aisle where you insert the cold air comes in, the hot comes out here. We'll take a look at a little bit more what that looks like. But this is a rack architecture, okay? Low density, 0 to 9, medium, 9 to 20, and high density is about 20 kilowatts plus. That metric is simply how much stuff can you put inside of there? How much stuff can you put inside of a rack, right? Right now, the common average is between 8 and 16 kilowatts. I don't know if you can see this. There's a fun fact. In the AFCOM State of the Data Center report this year, 2025, the average rack density in the facility is about 16 kW. 9 years ago, when I wrote this report for the first time, it was about 6.1 kW. So I'm glad our industry is advancing. What you can see right now is that modern colocations are now kilowatts plus, and specialized colocations are designed upwards of about 300 kW. If you can raise your hand and tell me, do you know what this is, this rack right here? If you went to GTC, you may have seen it. And I'm glad you all are sitting down, and I'm glad that all of you are relatively new to this industry, because what I'm about to tell you is epic, and it comes from what Wade talked about. These are now going to be called megawatt class racks. This is the NVL 576. It has 576 GPUs spread across 1, 2, 3, 4 pods. This rack is about $15 to $20 million and is going to consume upwards of 600 kilowatts per rack, more than 5 times the 120 that are being used by the current Blackwell B200 racks. Now, one of my partners, and I'll show you a picture of this, Scott Data Center, they upgraded from a 10 to 20 kW rack to a rear door heat exchanger, 60 to 70 kW rack. But if you can imagine 60, this is already 600 kW. Now, if you're sitting here thinking, how am I going to deliver 600 kilowatts of power into one rack? This is the future. Jensen is going to be releasing this, so this is something you need to start thinking about. But again, understand that the average rack density is, again, between, I would say, between 9 to 20 kW. But this is important. This is what a rack looks like. We'll keep it up here because I think this thing is really neat. Now, rack density in the age of AI. This is an all. I'm going to keep this as brief as I can. This is it. This is actually one of our racks. It's running Apollo, our system on there. There are 6 DGX units. This rack cost about $2 to $3 million to produce. Each DGX has 8 H100 cards. Each card is about a very nice luxury Toyota Corolla. There's 8 Toyota Corollas in there. I don't know. It's a good parallel. What's really fascinating is this right here. This is a Motivair rear door heat exchanger that leverages liquid cooling, right? It's really, really great. And a rear door heat exchanger, it's basically it's a radiator. It's a radiator in a car. That's all it is, right? Hot air, process it, get cold air back out, and then boom, right back into the facility. Now again, this architecture right here, NVIDIA allowed only 4, 1, 2, 3, 4 per rack. But Scott Data Center proved out that they can do all 6, and guess what? NVIDIA rewrote their reference architecture, and now this is live and active, and we're going to be deploying just sub of 1,000 GPUs in what was traditionally a normal, like a co-location data center. Actually, I think there's a session that they're going to be doing co-location to GPU as a service. You got to check it out. But this is what this looks like. These are AI GPU-enabled racks in the age of artificial intelligence. Look. Just to give you a perspective, think about it really quick. If the average rack density is 16 kW and one of these takes up 10.2, how are you going to put one of those in a rack, right? It's just going to be one and then just a whole bunch of blinking panels, and that's all you got. It's not going to work that way, so you need ways you can make your rack a lot more efficient. Okay, what else other than AI and GPUs goes into a rack? This is important. So you have to have servers. There's different types. So hyperscale, if you've heard of the Open Compute Platform, OCP, Meta, Google, sometimes they design around their own systems because they're single tenant. They can do that. That's their data center. It's all their stuff. They can manage it really effectively. Inside of there, you have accelerated performance, different form factors, power ranges from a few hundred kW to 1,000, and this is a chassis. So this is more of those pizza box servers that I talked about, and the one right below, these are called blade chassis. Each one of these you see sliding out is a server. I love blades. I deployed them a lot when I was partnering with Cisco, NetApp, and all those other wonderful folks. I like them because they're converged infrastructure. The wiring is really pretty, and you can put a lot of them in a rack, and you can do a lot of compute with that kind of architecture. So these are the servers that go inside of an environment. Now, storage is another piece, and this is a big one. Moore's Law, I was really debating on whether or not I want to include it in here because some people are having a bit of an issue. Moore's Law basically translates to the amount of transistors and chips you can put on a board, doubling every 2 years, but you can do so economically, not just putting them there for the sake of putting them there, but also economics work for you. Right now, Moore's Law is experiencing a little bit of an identity crisis because it's either accurate or it's not, depending on the technology. So, whether you like it or not, that's fine. But driving trends, all of you being connected, Internet of Things, and obviously ChatGPT, the amount of data it's producing is incredible. Solid-state drives is another really popular one. I love SSDs. Back in like 2010, 2011, they weren't as popular because they weren't as resilient or reliable. Now they're infinitely better. No moving parts. Much less heat. They are lighter, so your storage arrays are a lot more effective. I'm a big fan. And obviously, performance is driving storage closer to the server because of AI. And that's a big part of it because mainly people want to do AI where their data lives. And this is especially true for things like inference. Don't have time to go into training versus inference. If you're curious, you can ask me about it. But that's where the trends are going. And again, this hyper-converged compute series, if you saw this server, this is an example of a hyper-converged, right? Really all this stuff in one chassis, all of it working for you. So that's storage. This is like the nervous central system of an infrastructure. And honestly, sometimes we don't talk about this enough. Many facilities right now operate at with 1 gigabit network speeds or 10 gigabit network speeds, which are fine for SQL servers. Citrix, VMware, and Exchange, that's fine. If you start to talk about AI and inference, you need to start looking into these higher bandwidth 100, 400G, and even more. Everything is connected. A lot is being done over wireless communication, which is fine. But obviously security and cybersecurity over the network, because we are so incredibly distributed, is important. And you know, honestly, I forgot to talk about this last year, but undersea cables. This is a big one. I'll give you an industry secret. If you want to know where the next data centers are going to be built, follow the cable. Follow where they're going to be laying them, which markets are coming in, which coasts, whether it's Canada or Africa or Europe, and you're going to know that there's going to be a booming market, because you know, without fiber, without connectivity, obviously without power as well, it's very difficult. Right now, despite what people think, why we've heard in the news around undersea cables, 99% of all international data traffic is carried by those undersea cables, so they're very important. Again, if that's something that you're curious about, I would recommend taking a look at who's laying them, where they're coming in, because you're going to get a chance to see where these new facilities are coming online. All right, GPUs. We got to talk about this briefly. This is a part of that IT hardware that's coming in. It is a massive, massive market. That's not just the big green machine. Okay, NVIDIA is great. They're producing, they're leading, because they bet very early on that the majority of workloads are going to be moved to GPUs, and boy, were they right? Good for them. But NVIDIA is not alone. Intel and AMD are going to be pumping a lot of dollars to what's going to be a more than $80 billion industry just in the chip market alone. You're going to require re-architecture. Every data center is going to become an AI data center. It completely depends on how fast you can get there and how you can support your customers. So again, you have to look at high density power racks, you have to look at new cooling solutions, aisle containment, and again, what's really cool about these kinds of architectures is that when designed properly, you can actually use up less floor space, have less equipment on the actual floor, and so on. So GPUs are going to be really important. I'm going to make sure I'm pressing the right button, not the laser pointer. In this kind of environment. Do I have to move closer to my computer? No. Next slide? No. We have to do it manually? Okay. That's okay. We'll do it manually for now. I think the battery ran out. Site selection. Okay, once you actually pick out what goes into the environment, is my clicker dead? I think my clicker's dead, unfortunately. So when you actually pick out your facility, there's a couple things you have to look at. So at this point, everybody, let's quick level set. You know what goes in a rack. You know what density is, you know what servers, storage, all that stuff. You're good. You're good with the rack. We're good. Now let's build a data center together. Let's do this. So at this point, you're like, I know what goes in my rack. Now we got to pick a place. We got to pick a site. These are all the key drivers, right? Power, water, fiber, incentives, and the use case. Am I doing it for inference? Am I training big models? Am I going to be a co-location that I need to be in market? Am I building for Google, for example? Those are really important considerations to understand where you're building this stuff. Now, there's threats, challenges, however you want to put it, but these are really critical to understand. So natural disasters, visibility, railway, roadways, air traffic, neighbors and communities, right? We have the not in my backyard challenge sometimes. Underground utilities and unfortunately geopolitics as well are threats in terms of building environments and putting the stuff out there. So again, these are just some key considerations. Now, when you actually, all right, we've picked a site. We picked a site. We know what we want to do. Let's put some stuff in there. So these are all of the architectural key components. And please understand really quick, if there's like a data center expert here that's judging me right now, that's fine. I don't mind being judged. But this is not an all-encompassing list. There's other things to consider in here. This is why it's a 101. So data hall, mechanical, electrical, plumbing, telecom, network space, IT support space, and office, and a dock, and logistics. A lot of people think it's just a warehouse with a whole bunch of rows and servers. It's not, right? It's a building, it's a facility. There's a lot of stuff that does go into it. So again, just kind of keep in mind that. So when you pick, all right, so at this point, we know where we're building. We know our architecture. We know all the stuff that's going in there. Let's talk about inside of the building. What does it actually look like and what does it represent? So we're going to talk about the building form. First of all, I worked at Switch Data Centers for 4 years. I grew up in this industry. I got a network engineering in undergrad and network engineering and telecom management. And I literally, when I graduated college, I worked in the data center space right off the bat. So I'm a native here. I wasn't adopted into it. I love modular systems. I really do. Traditional brick and mortar are great. That's what a lot of maybe single tenants are. But when I say you can modularize anything practically, you can. Office corridor, office space, a hallway, an entire cooling unit, a power unit. And what this allows you to do is to buy a big campus, a big amount of space, and build out in modules, build out intelligently to make sure that you're actually supporting your environment. And oh, they gave me batteries. This is why I love the attendees in there. The audio people are like, Bill, you'll be all right. But all right, well, I will see if I want to put these in here or not. I just want to keep going. There's a good flow. Thank you so much for the batteries. So that's the form factor. I love modular systems, like I said, because you get a chance to build stuff out in puzzle pieces. As you grow, your infrastructure grows. You learn something called an envelope permit. That's what a lot of people do. An envelope permit means that I think this is going to be 300 megawatts, so I'm going to permit for 300 megawatts. I think I'm going to need this much space, but really you might be only starting with 50. But you have the capacity to grow, and these modular systems allow you to pretty much scale as you need to. So now you are inside the building. All right, you know what you're doing. You got your modules. Now let's stand inside of a data center hall really, really quick with me, okay? What you see over here is a pretty traditional architecture and a building form environment. So you can see all the way to the left, it says CRAH, computer room air handler. That's it. Or you might see something known as a CRAC, C-R-A-C, computer room air conditioner. We'll go into what those are in just a second. But effectively, you can see me or whoever's standing there raising their hand. That's how tall it is. And so you have the computer room air handler that processes the heat, right, and puts that cold air underneath a raised floor, and there's little grommets and little perforated tiles that allow the air to come in through the front and then exit out the back. And since we use physics to our advantage, right, we let the hot air rise, be collected right up there in the plenum, and cycled back to make it cool again. That's it. That's pretty standard. How tall is the stuff? Air plenums, that's where the air cycles back and circles back to be cooled again. Certainly the clearances, they're not all the same. They're not all the same. If you have like a taller rack or something along those lines, but this is a pretty good standard structure for you to look at. Now, inside of the facility itself, you have to think about where you're going to put this stuff. Okay, so you're in the hall now. You've got your, the containment, do I put it above the ceiling, which is fine in a busway kind of, or do I put it below the floor? And this is a new statement. Raised floors, because you could have raised floors kind of like this, or you could have a concrete slab, right? Raised floors are making a big comeback because of liquid cooling. You have to put the water manifolds somewhere, right? You can put them above the rack, or you can put them beautifully underneath the rack. And that's a really great way to do it. That's my favorites. So if you've got a good raised floor architecture, you can put it underneath, and it's going to work out really well. Go ahead. So this is the stuff that goes in there. Raised floors, like I said, are making a big comeback because you can put the water manifolds right underneath, and it's very, very effective. But if you take a look at this, this is what it looks like. And in this specific image, it's still raised floors, but you can see where the power equipment is, where everything else is. So this is a building form with everything else that's fundamentally in it, all the other power components and so on. So let's keep going. Okay. How many of you have been inside of a data center? Cool. How many of you that have been inside of a data center, it just looks like a warehouse? You can raise your hand, don't be shy. Okay. I had a chance, like I said, to work at Switch Data Center for 4 years, and they build really cool facilities. I really do enjoy them. So let's take a look. A lot of times in our industry, people think that data centers are these nondescript buildings off the side of a highway. They're beautiful, and they're really cool. Check these out. So the architecture of a building, it can be varied. These are all data centers. So I'm going to look at my notes here really quick. The one in the left, the upper left, that was opened back in 2005, that is the Barcelona Supercomputing Center, built in a former 19th century church. That's epic. The one that is just to the lower left, that is Naver, Korea's leading web portal, and they built a data center into the foot of Mount Gubong in South Korea, where they host their online customers' profiles. The one in the middle, that's called the Bahnhof Data Center in Stockholm, and it was opened in 2008, and it was a former nuclear bunker. Actually, that is straight up out of James Bond. Like a villain lair. I think that place is so cool. And upper right over there, you could see my office. It's just one floor below. I was on right up there. That's the Switch Pyramid out in Grand Rapids, Michigan, and that is a classic reuse of an iconic building that was once used by Steelcase. They make manufacturing for chairs and really high-end office. And my former boss, Rob, he's like, I'm going to make that into a data center, world-class hyperscale. And he did, and it's a really cool campus. I really do recommend it. And the one on the lower right, well, that one is called the Amsterdam Data Tower. It was recently taken over by Digital Realty. It's got 13 floors of space, about 9 megawatts of power. So please understand that data centers aren't just warehouse-looking types. They are beautiful. I've worked with so many architecture firms that design really, really neat buildings. So I recommend that when you do some tours that you appreciate the architecture of these facilities. Now, when you do build them, not all data centers are pyramids. Not all of them are built into churches or mountains. You need to think about this stuff. It's very, very critical. So seismic loads, wind loads, hanging loads, slab strength. Just because it's a concrete slab doesn't mean it can handle an infinite amount of weight. So that's really, really important to understand. Tile strength, that's an important one. So just to give you a perspective, so our big partner in Omaha, Scott Data Center, their tiles support 5,000 pounds per square foot. That is why they can support 6 DGXs in a rear door heat exchanger type of an architecture, because it's heavy, but it can support the strength and the weight, the slab flatness, and you want to make sure you have structural systems that are all in place. This is something a good engineering firm will help you with, but absolutely all really critical considerations you have to worry about. Now, this is it. This is it. We functionally built a data center. We got a site. We got IT. We got all the stuff that goes in it. Good job. Now, you, as my Data Center 101 operators, well, you're going to need to learn some terminology. You're going to need to do it because you're going to be hearing it a bunch. You're going to need to know it. So at a very high level, we're going to talk about these really important concepts. These are all really important, non-technical definitions: redundancy, reliability, availability, mean time between failure, mean time to repair, concurrent, maintainability, and fault tolerance. There are other terms. There are many other ones. But for a 101, this is going to be pretty key. So let's dive into these just a little bit. So first, we're going to cover redundancy, and this is pretty straightforward, right? So N is the number of components or systems needed to meet load. So that's the number of systems you got. R is the number of components or systems beyond N in order to provide normal function during a maintenance or a fault, right? And the common one is N plus 1 level of redundancy. And drum roll, the purpose of redundancy is to improve reliability. So N is your one primary main system, and plus 1 is a system that can take it over if there's a fault or if there's an issue going on. Now, looking at reliability, this is something that is measured, the ability to measure, this is measured in time, in units of time, but the ability for a system or component to perform its required function in a stated condition. Now, please, food for thought, don't just take this number at its worth. Make sure you validate, well, what is the time frame? Is it like 3 days or is it 2 years, right? Because you could have some pretty different reliability metrics. Now, the more reliable your system, you're going to be able to have a lot more availability. Now, this is actually really interesting. You probably have seen this. This is measured in nines. 5 nines, 2 nines, 3 nines. You're going to hear a whole bunch of it. But availability is the proportion of time a system is in a functioning state or condition. And the ability is, again, talked about often in nines, 4 nines, 5 nines, even 6 nines. Now, that is, when you talk about that level, that's expensive. That's like seconds of downtime a year. Very, very, very expensive. So again, just kind of food for thought in terms of what you're designing. And again, it's all dependent on your use case. So let's kind of go into what happens inside of a facility. If there's a failure, if something happens, These are really important metrics for engineers to follow, right? So mean time between failure is, as you can imagine, the average time between the failure of a system. And the mean time to repair is the average time to repair a failure, thereby restoring normal operations. Very important terms. You see this with every piece of IT equipment, whether it's a rack, power distribution unit, across the board. This is something that's really, really important to understand because it allows you to understand mechanical equipment, what goes in, what's functioning and what's not, and again, helps you build trends over what's in there. Concurrent maintainability. This is an important one. So one system, component, or distribution path can be taken down for planned maintenance and without affecting the primary function of a facility. So this is basically being able to take down, let's say, a chiller or a power unit or a generator to do maintenance on it, knowing, right, N+1, that you've got an architecture that can support the rest of the environment. The next one is going to be fault tolerance, which is similar to concurrent maintainability, but in this case, it's a fault, right? So one system, component, or distribution path can fail without affecting a primary function of the facility, and systems must be self-healing following the fault, which means that if there's a fault, if something happens, you have a system that's capable of repairing itself, or at least an engineer that can come out and look at it. So again, very similar to concurrent maintainability. Basically, you have a system that can take over if there's maintenance or if there's a fault. Let's talk about design standards. This is going to be a big one. You're going to hear about Uptime Institute. You're going to hear about tiers, all of that stuff. Uptime Institute developed levels, providing guidance for achieving desired levels of reliability and availability when you implement different types of components and system levels. So there's a new one called Tier 0. It's the crypto miners, basically, where they don't look at the redundancy of physical workloads. They look at the redundancy of software, right? If my data center fails, I don't care because I could just move the software to another one. I can gab like an hour or 2 hours of downtime, it doesn't matter to me. Now, in those environments, these are crypto miners, for example, they won't have N plus anything. It'll just be N, and for them it works. It's not very common, so you're going to see more of the 1 through 4, and this is what they look like. It goes back to like the 9s and how much stuff you have in the environment. So this graph is very much available right now. It's tiers 1 through 4 from the Uptime Institute, and you just take a look at that. We don't have to dive into it too much, but distribution path, concurrent maintainability, fault tolerance, all the things that we heard about today, continuous cooling, and so on. And you can see tier 1 and 2 and 3. Those are great facilities, right? You can get even tier 3 plus, but once you start to get to tier 4, there's a lot of redundancy, a lot of concurrent architecture there to keep it up. Those are going to be your most expensive or more expensive types of systems, where your kilowatt per hour or how much you pay for a rack or whatever's in there is going to be a little bit more pricey. But that's it. That's the tier levels. Data centers will have their own classifications, and you can pick the kind of architecture that you need. All right, we're going to go into the actual mechanical hall because we've got to talk about cooling and power, and we're doing good on time. So inside of the facility, this is the mechanical data hall cooling. So we have these hot aisles and we have the cold aisles. A lot of times there's something known as containment. When you get to the showroom floor, you will see examples of containment. So you don't just have to listen to me. But inside of that environment, you can see that the hot air goes up, the cold air goes in through the cold aisles. You can see the perforated tiles, like I said earlier, that allows for the cold air to go up front. Now, the one thing you can see where it says hot aisle right there or cold aisle, sometimes you will see doors, special chimneys, or containment that allows you to really contain and maximize efficiency so that you're not losing any of that air or heat. You really are containing it. But in that sense, we need to talk about conventional cooling strategies. So this is what you'll see: chilled water, packaged air conditioning units, crack and cray units. And again, you can see all the way to the left, the main difference between a crack and a cray is that one uses refrigerants and compressors, and the other one uses chilled water and control valves to cool the environment. One thing I want to make sure everybody knows, is that when we're in the age of AI, just please understand this, we're reaching the limits of how much air can dissipate heat from mechanical equipment. Now, this is not Bill Clayman coming here and saying that airflow is going away. It's not. But when you start to take a look at new systems, especially AI, you need to look at a new level of cooling, certainly. So these are all the big components that go into a facility to do some of that mechanical cooling in the environment. Now, I had a slide last year that was just way too technical about something known as direct and indirect cooling. I've got one slide. It's going to give you a little bit of a comparison so you can take a look at it. But inside of it, in a facility, you've got direct and indirect cooling methods. Just very, very briefly, in a direct, it passes through these pads, cooling by evaporation. There's pros and cons to it. Yes, there's direct air content, so you have to make sure concern yourself about contamination, for example. How do I filter that air if I need to? Very efficient, low initial cost, simpler design, and it's great for dry, low contamination environments and cost-sensitive scenarios. The other one is called indirect evaporative cooling, where it passes through a heat exchange. So it's a bigger unit. It kind of goes up. Sometimes they're on the ceiling or somewhere outside the facility. It passes through this heating unit, and it goes back into the facility. It's indirect. It's minimal to the indoor humidity, so you don't have to manage it too much. With the other one, you do have to manage humidity inside the facility a little bit more. It's a higher investment cost, but again, if you take a look, there's specific use cases of why you deploy it. So if you're worried about contamination, you need stable humidity, or you have a specific type of use case. Last year, I had just charts up there, and people were like, Bill, there's a lot of colors. I don't know what that is. So just kind of food for thought, and you're always welcome to do your own research. Now, the question that I usually get is, Bill, well, how do you know what to cool? How do you know where your hot spots are and your cold spots? And you're going to learn about something known as computational fluid dynamics. This is what that is. This gives you the opportunity to see, where do I have hot spots? Where do I have efficiency or inefficiency? And this is the difference between an open space, right? Cold supply provided, but there's still hot racks, and versus containment, right? In that situation, you are containing that airflow and you are managing a lot more effectively. So I love computational fluid dynamics because it gives you that, a visual of where you could be more effective, how you can optimize airflow. And believe me, what was it Wade said, every watt matters. That's very, very true, because in this case, you can save a lot of money by deploying an architecture more effectively. Let's talk about power. We're coming into the tail end. We're doing really, really good here. This is what it looks like. It's standard. It's very, very typical kind of a design. You got your facility over there, substation, transformer, generator, power coming in. It could be natural gas. It could be eventually nuclear one day, but whatever your base load of power is. By the way, you're welcome to take pictures. This session is being recorded. Hey, everybody. And you're welcome to get these slides. Just send me a note, send me a DM on LinkedIn. I'll get you these. I know that these are useful, and we're going like 1,000,000 miles an hour. Inside of this environment, let's take a look at what a very redundant electrical design consideration looks like. This is just one of them, okay? This is an architecture that's very, 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 very resilient. You've got two different utilities, completely separate, two different generators. ATS is automated transfer switch. If there's an issue ever, it'll switch between the two. The generator or the utility goes back into an uninterruptible power supply that goes into PDUs, power distribution units, two completely separate lines. This is more expensive, right? This is not always the case. In some situations, you might see just one utility, but multiple generators, for example, right? If you only have access to one utility, that might be the case. This is a design. This is one of the electrical design considerations that you might look at. This is one that's highly resilient. But that's a system plus system topology. I have others, but again, we didn't want to get too far into that. Now, the other aspect is, as far as this is concerned, is what kind of power are you getting in this environment? I mean, tomorrow, I'm going to be on the keynote stage with the head of Google's clean energy decarbonization and the leadership from Kairos Power, and we're going to be talking about their nuclear reactor that's coming online in 5 years. Not 10, not 15, in 5 years. So I think like between natural gas and nuclear, that's going to be a big part of our future. But there's a lot. There's a lot of options out there, geothermal, fuel cell. People are looking at tidal wave technologies where you can capture some of those currents as well. But it's a much more sustainable future where we're going to look at clean energy sources, and a big part of that is going to be nuclear, natural gas, anything that gives us a base load of power, because honestly, the sun doesn't always shine, the wind doesn't always blow, so we need that base load of power coming from somewhere. This is actually we're gonna be starting to wind down. And remarkably, this is some closing. I know I told you this was a lot. This was literally a 101 masterclass. I'm not kidding. We built a data center. Good job, team. Yeah, you're all data center architects and engineers. Congratulations. You get to get the Bill Clayton stamp. I don't know what it's worth. But you've done it. You've done it. You know what goes in a facility. You know what goes in a rack. We talked about density, cooling, power. We've talked about the structure of the hall, what goes into the mechanical equipment, what cooling looks like, what power. This is it. This is the entire structure of a facility. Now, some things I want you to be very mindful of as you walk around the convention hall and you go to all these sessions. None of this is changing. None of this is changing because we're only pushing forward with the rise of AI, nuclear, robotics, and more. Data centers are going to be everywhere. Now, we're no longer a well-kept secret, which was always something that bothered me. We are very much in the spotlight, and we are having a moment. Like I said earlier on the keynote stage, I met a gentleman, a young man who's 18, 19 years old, and we were talking shop, and he's like, what do you do? I work in the data center industry. And he's like, cool, servers and ChatGPT and stuff, and like buildings. I'm like, yeah, the first time in my life I didn't have to tell somebody what is a data center. And that in itself is extraordinary, at least in my eyes. There's still talent challenges out there, talent shortages. I don't know why they decided to call me this. I'm a geriatric millennial. I don't think that's a necessary term. You can call me an older millennial. But you know, I try and work with this next generation to inspire them. And finally, we're having college degrees, certifications, entire courseworks designed and developed for data centers. I lecture at the USC School of Engineering, and I work with mechanical, computer, civil engineers, and my job is literally to tell them how you can apply your skill set to our industry. And I really recommend and challenge all of you to inspire somebody young to come in, to learn about this industry and space, because it is really, really cool. That's why I want you to educate others and inspire them, because this truly is a wonderful community. Let me see, I think, oh yes, one more important note. All of you should have access to this report. It's updated every year. This is the AFCOM 2025 AFCOM State of the Data Center Report, written by yours truly, written for the past 9 years. A lot of really wonderful information in there. It is market validated. It is reviewed by the Informa market team. There's a brilliant PhD that makes sure that all the data is market viable. If you don't coming off, is that what's up? Yeah, all right. Why don't you get the hook out too? All right, so this report is great. You're welcome to, if you don't know how to find it, if you can access it, just find me. Oh, I'm not going to be able to give it to you in a hallway, but find me online. I'll be able to pass it over to you. And I think the most important part is just let's keep this conversation going. Find me on whatever social media you want. I'm pretty active on LinkedIn. Don't be shy. Find me in the hallway. Take a selfie. Make sure you post it. Guys, this was a 101. We are literally 30 seconds away from ending. I don't think we're going to have time for Q&A because this room is giant, but I'll hang out for a minute if you have a question. Thanks so much for building a data center with me, everybody.